Okay, so we're going to move on to chapter 4 now. The study of the Schrodinger equation in 2 and 3 dimensions. I don't spend much time in 2 dimensions, but I'll give you an introduction to the next step a little bit beyond 1 dimension and then 3 dimensions. And this will get us started on the hydrogen atom. We'll take the hydrogen atom is completed in a later chapter, so we'll be taking some reading from a later chapter. So you'll understand how the hydrogen atom goes. Okay, so we begin with the time-dependent Schrodinger equation. Let's start for a free particle in 2 dimensions. Okay, so the use Cartesian coordinates. And so let's begin by writing it down in Cartesian coordinates, and we'll see that there are cases where we want to do something other than Cartesian. Here's an example. So the wave function is now a function of the 2 Cartesian coordinates in time. And so here is the time-dependent Schrodinger equation. And I'm going to introduce also here a technique which will be useful as we go through this. For example, if we go extend this out to 3 dimensions, consider a free particle in 3 dimensions, we have a function of x, y, z and time. So we've got a function of 4 variables. So things are getting to be a little bit unwieldy. So we need some techniques for how to handle equations with multiple variables. And so the one that's introduced there are lots of different techniques. But we're going to introduce the idea of separation of variables for solving partial differential equations. Separation of variables doesn't work generally, but it does work for certain specific cases, and we're going to use it in those cases where it works well. Here's an example of a separation of variables. We actually did it before in 1 dimension. The idea behind the separation of variables is to take a function of 2 variables and write it as a product with 2 functions, each of 1 variable. So this is an example in 1 dimension. So let's try this. Go back to the free particle in 1 dimension, or actually the Schrodinger equation generally in 1 dimension. So we had, for example, we started with this. We write down the problem for some potential. Okay, and then let's try the separation of variables. Substitute that into this equation here. So try psi of x and t product with 2 functions. I say in general, it's not guaranteed that you're going to be able to get a solution. But in this particular problem, it works as long as this potential energy is not a function of time. Potential energy could be a function of time. If, for example, it's the potential energy from an electric field. Say the phi field, that depends on time, for example. So if B depends on time, then the separation does not work. But if B, like the simple harmonic oscillator or particle in the box, potential didn't change in time. So this separation is going to work. This will work if B of x doesn't depend on time. Okay, so I'm just stating this. You'll see maybe why this is true here when we just try it. Okay, so when we substitute this into here, the time derivative acts only on so I have 2 functions here, capital X, the coordinate X, and then capital T of the coordinate T. I have 2 functions. The product of those gives me psi. When I substitute this into here, the time derivative acts only on the capital T. So on the left-hand side, we have it's a function of only 1 variable, so in fact it's derivative. for partial derivative there. And then on the right hand side, we substitute this into here. Function of x, Hamiltonian is going to act on that part as a function of x. This function of time is just going to pass through these operators. So we get t of t times. I'm going to change the derivative here. Derivative of x because x depends only, the function capital X depends only on the coordinates little x. Okay, so far? Okay, now I'm going to divide by the wave function. Divide both sides by the total wave functions. So I'm going to divide by the product. Left-hand side, when I divide by the product, x bar cancels out. So I have I h bar 1 over the function of t. And when I divide the right-hand side by the wave function, the t part cancels out. And I have 1 over x. Now let's remind ourselves, going back to this equation, nature of a differential equation, especially when it's a function of two variables. We have the left-hand side as a function of x and t, and the right-hand side is a function of x and t. So this is a function, and this is a function, and the two functions have to match for all x and for all t. That's the meaning of a differential equation. Different than an algebraic equation in x, for example. You want to solve for the zeros of the quadratic. You're looking for particular values of x that satisfy the polynomial zero. This is a different kind of thing. We have a function of x and t on the left and a function of x and t on the right. Okay, then we go through the separation process. We have now a function of x and t on the left and a function of x and t on the right. Possibly, but notice there's no x dependence over here. There's only a t dependence. If we're following our separation. So this depends only on t. There's no x dependence left. And on the right-hand side, it depends only on the x coordinate. Doesn't depend on time. Does it? I'm sorry. Depends only on x. So this side depends only on t, not x. This side depends only on x, not t. There's only one way that you can have that to be true. Both of those true. The left-hand side depends only on t, not x, but has to be equal to something that depends only on x, not t. And that is if both sides equal a constant. You see that? It's an important step in the separation of variables. This has to depend only on t, it can't depend on x. If we change x over here, this can't change. So that means that with respect to x, this is a constant. When we go over here, we say, well, this depends only on x. If I change t over here, this can't change, so it's constant with respect to t. But they're equal to each other, so they both have to be just constants. Can't depend on x or t. Interesting step. And sink in. It's a clever step. So the conclusion is that if this guess is going to work, then it has to be that each of these equations equals a constant.
Do they have to be the same constant?
Yeah. Yeah, because they have to be equal to each other. Same one constant. No x or t dependence left. So this is called the separation constant. kind of intriguing. So let's see where that leads. We haven't yet determined that this gas is going to work. But if it is going to work, then this has to be true. That this and this have to equal the same constant, independent of x. It is going to work, but we're following the logic of it. See what we count. Okay, so now let's take that first one here. We're going to look at this. It's equal to a constant. So IH bar time derivative of t, factor t, with respect to t, is equal to some constant. Okay, so what's the solution to this equation? It's a very simple equation. The derivative of a function is proportional to itself. Only one function that does that. The exponential function, right? So the solution to this is going to be another constant. Let's call it T0. E to the minus I times this constant over H bar. So we substitute this into here, This satisfies this, and then there's this new constant here that we have to determine yet. Some constant. See how this works? Derivative here with respect to time, we get a minus times this constant, separation constant divided by H bar. We multiply by IH bar, that just gets constant. Okay, what does that look like? This function. You've seen it before.
Gaussian.
No, it's not a Gaussian. It's like Gaussian has a square.
It's like the solution for the time in the pure modes.
Pure mode. This is a pure mode. If the constant over H bar, let's call that, then what is the constant? Separation constant. E. It's the energy. Okay, so in that case, this function, we still have this kind of multiplying constant. We got to figure out what that is. E to the minus I omega t. Pure mode. Well, we did that before. It's a different way of getting to a pure mode solution, right? The pure mode was something that we tried, we guessed, particular solution to the time-dependent Schrodinger equations. We guessed a pure mode so that all the parts are changing at the same one frequency. So we guessed this before, but now this comes out, drops out as a result of having tried the separation of variables. So we're just kind of going back over the same territory again. We got there a different way, same place. Okay, so that's this one. But we've identified the separation constant as the energy. So now we want to look at the second equation, which is that this constant equals this thing. So can I erase this part? So the second of the two equations now, so what we did was we took one equation and two variables, and we got two equations, and each in a separate variable. So we got this one is equal to energy, and we're going to get this is equal to the same energy. So the second equation we've identified the separation constant as the energy. I set this to the energy, and I'm going to multiply by capital X. What is this equation?
Sorry, just
Right.
Wouldn't the one over capital X cancel with the X?
No, because there's this derivative there.
Oh, never mind.
Yeah, if it were just the potential, then yes, but there's a second derivative. So this is the second derivative of x divided by x. So, yeah. It's the Hamiltonian. Pardon?
It's an operator Hamiltonian. Well, that's connected here.
Yeah, this is the Hamiltonian acting on some function is the energy times that function. What is, we gave that equation a name. We had this, we named this differently.
Oh,
Yeah, you did close, it's an eigenvalue equation, but we gave it a specific name right at the beginning of chapter 2. The time independent Schrodinger equation is just in a different value. So we call that psi. The time independent Schrodinger equation. Right, because we got to the time independent Schrodinger equation by positing the pure mode solution. We want to try a pure mode solution, make out as the time independent Schrodinger. And so when we do the separation of variables, we get actually the same thing we got before by doing the separating out the time and the x coordinates. So it's actually not a new thing, it just looks new at the beginning. This looks odd, but we did it before. When we posited the particular pure mode solution. Okay, so this is actually familiar ground, just didn't look like it at first. So yes, ma'am.
Where did the one over capital X end up?
I multiplied both sides by that. So I multiply, take this equation, this is equal to E, and then multiply by capital X. Cancel that, and gives you E times capital X. Kind of clever. Doesn't always work, but it often works. In fact, we're going to use it in a lot of cases where it does work. This trick. In particular, it works as long as this potential doesn't depend on time. You can see what would go wrong if this depended on time, then this statement would be incorrect. Not only depends on x, but also on time. You can't do the separation. So that's what would happen. But usually, in the problems we're doing, potential energy does not depend on time. Doing a particle in the box, or simple harmonic oscillator, or something. Okay, so that's introducing the separation of variables into a problem that we've done before. It's something like what we had seen before. Now we're going to try the separation of variables going back to the two-dimensional problem. So let's do a 2D free particle. That's what I wrote up originally. And we're going to tackle this with the separation of variables strategy. We're going to try this free particle first. Okay. So now we have a function of three variables. The first thing we're going to do is try to peel out the time dependence. Separation of variables will give us this pure mode again. So the pure mode, the separating out the time dependence. You can do it either way. You can see it as a separating out the time dependence and then see what we did, or you could just posit the pure mode. Either way, you get to the, you go from the time dependent Schrodinger equation to the time independent Schrodinger. Where this energy here is related to that pure mode frequency. That's usual. so this step is done either pure mode or do a separation of variables, separating out time dependence. Either way, you get the same thing. You end up with this. And we've seen this before, time equation, except we haven't seen it in 2 dimensions. Yes.
So if you try that, if you try and plug it in, get to that.
Yeah. We did this in general. We started off with the time-dependent Schrodinger equation. We put this as a pure mode test, and then we got this equation. That was back at the beginning of chapter 2. Okay, but you can see what's going to happen now. What's the next thing we're going to try?
Get X out.
Yeah, we're going to separate X and Y. We have a function first of 3 variables. We do one separation, we get a function, we get a differential equation of 2 variables. Trying to do another separation into X and Y individually. And see what we get. We'll get 2 equations, one for X and one for Y. They have to work together to give a complete solution. We'll see what we get. Okay, so let's do this. Let's try. I guarantee you get a solution, but in these kinds of problems, something you should anticipate. I'm not going to try something to fit in normally. Yes, sir.
It was just about the letters, but I got it.
Got it? Read my writing. Okay. So I'm using the capital X to denote the function of little x, capital Y, function of little y. And psi is the product of those two gives us the complete wave function of 2 variables. Okay, so let's try it. We're going to substitute this into here and then divide by the wave function again. So we do this and then divide both sides by psi. Full wave function product. So when we do that, we'll get E is equal to minus h bar squared over 2m over x. Second derivative. That works. Okay, so now we want to group X is on one side, Y is on the other side. Doesn't really matter where we put the E. Put it in here, actually, it doesn't really matter. So I'm going to keep the E on the left hand side. I'm going to bring the X part. Okay, same strategy here. I'm trying to get X on one side, Y on the other side. Not have it mixed up at all. So we can get all the X terms over to the left, all the Y terms over to the right. We have this constant here, but it doesn't depend on either X or Y, so it doesn't matter where we put it. Same strategy here. This depends only on X, not Y. This depends only on Y, not X. And so both sides have to equal a constant. The constant is different than the one before. It's a constant that doesn't depend on X or Y. See that argument again? It's the same argument. Really very convenient to do this. Because now we have 2 equations. Same constant, the separation constant. The same, so we have two equations, one in X and one in Y. That's why it's convenient, because we started off with an equation in 3 variables, and by this process, we've gotten it down to now, we did, time came out, now we have 2 equations. They're connected because those 2 equations have to equal the same separation constant. Now we have 2 equations, in one, each in one variable. Okay, so let's see how it goes. It's going to be easier to start with this one. We have 2. Let's start with this one. And we'll multiply by x over y. Oh, minus. QM over h bar squared. I haven't given it a name yet. Just taking this and do a little rearrangement, bring the capital Y over here, and we bring this minus, we multiply by negative 2m over h bar squared to get it over here. And we'll write it in this form. This should be a familiar equation. Know the solution to this. Second derivative is something times the same function. Either a real exponential or a complex exponential. Right? I could write it as a trig function. Cosine and sine both satisfy this, but what we want is to have something explicit here. This constant, let's suppose for a moment that this constant is positive. We'll find out that it has to be positive. So if it's positive, then what's the solution? E sub constant times e to the I kx, where k, see this k squared is minus 2m over h bar squared times constant. If we take the second derivative of this, oh, it should be y here. Take 2 derivatives of this gets you I k squared. In other words, a negative k squared. So we get 2m. See, yeah, we get a negative k squared here, and that equals 2m over h bar squared times the constant. And I'm going to use a subscript here because we're going to have a need for a similar k for the x equation and a name for that one. So we're going to, this separation constant looks like this. We're writing it in terms of another variable, ky. So writing it this way makes it look like, oops, I'm sorry. There we go. That's what I meant to say. There we go. That's it. What does this expression resemble? Kinetic energy of a plane wave, right? But it's only the y part. It's not the full thing. It's just one dimension. We saw this before. This is like an energy, but it's not the full energy. Here's the full energy. It's part of the energy. So this constant is called h bar squared ky squared over 2m. Let's just call it that. Kind of awkward, but we could name it like that. You could call it the kinetic energy in the y direction, capital K in the y direction. Call it that. Okay, so the solutions look like this. We could also have a negative value of K here, which would be a left traveling wave. Positive value is right traveling, meaning positive in Y, heading towards positive Y. Negative value here would be towards negative. Yes.
If we suppose the constant's less than 0 and the negatives just switch everywhere,
Yeah, that's right. So if this constant is 0, that would mean that k would have to be imaginary, which would be a function that's growing exponentially or decreasing exponentially. We don't want to have that happen because we have a free particle. If the probability is growing exponentially in some direction, then when we try to integrate the total probability, you're not going to be able to do that because the probability is diverging in some direction. So constant less than 0 would be prohibited because psi of x and y would grow unbounded. In y. Okay with that? Okay, then we go back to the x equation. Let's go 1 over x double prime. And this is going to be equal to ky. Capital ky, which is h bar squared, a little k y squared over 2x. The implied portion of the kinetic energy. Okay, and this is a constant, right? I put the y here, it doesn't depend on y, it's just the separation constant. It comes into the y equation here. Okay, so all of this depends only on x, so let's rearrange these terms again. Let's see. Y. I got that right. Let's see here. Bring over here, bring over here, multiply by that, and yes. No double prime. Okay, it's the same equation again. We keep encountering this equation. It's a simple harmonic oscillator. The mathematical form of it is what we encountered when you did the simple harmonic oscillator in the beginning. Same mathematical form. Second derivative is proportional to itself and there's a negative. Again, we have this constraint. This must be positive here, or the function grows unbounded in some direction. So this has to be greater than 0. So it's actually convenient to find two constants, one for x and one for y. One is like the kinetic energy of x, the other is the kinetic energy of y. And this symbol will be in other words, h of y is h bar squared ky squared over 2m. H of x is equal to h bar squared h of x squared over 2m. And then the equation over here will give you this solution, and this equation will give you constant times e to the I kx times x. And then the total energy is just equal to h bar squared over 2m kx squared plus ky squared. The wave function is some constant times e to the I kx x plus ky. So we separated free particle in 2 dimensions, done each separately x and y, and we just have to be careful about how the separation concept works. And what we end up with is that these wave vectors in each direction have to add up this way to the total energy, which is related to the frequency. Okay, so the complete solution then of this type, all the parts back together then. Constant times e to the I ax x plus ky y minus omega t. H bar omega, which is the energy, h bar squared of 2m squared plus ky squared. Okay, and that's the solution. That is a solution to the free particle in 2 dimensions. That's a lot like what we did before. It's like a plane wave. But notice there's a k vector here. It has a component in the x direction and a component in the y direction. And remember, the momentum is h bar k. So we have a component of the momentum in the x direction and a component in the y direction. And we have just this relationship, h bar omega is equal to h bar squared over 2m, and this is like the square of the k vector. That's the dispersion relation that we saw before in 1 dimension, but now it's in 2 dimensions because k vector, right? K vector dot k. Remember, we had that. It looks at the generalization of the dispersion relation where k is a vector. And we could write that in this form. By k dot r minus omega t, where r is the position. K vector is this. And we have right this is the dot product. Kx plus kyy is the same as the dot product k with r. Right. Nice and simple. So this is just generalizing the plane wave. We had plane waves in 1 dimension. Now we have plane waves in some other in 2 dimensions, but we have a wave vector, which is related to the momentum of the ensemble. So it can be in some other direction, not just along the x-axis, but some other direction. It could be along the y-axis, it could be in the direction in the plane. Okay, so far with that?
For omega, is that h bar over 2m times k dot k?
Yep. This is now the dispersion relation for the Schrodinger equation for free particle in 2 dimensions. In 1 dimension before. Now it's 2 dimensions. Actually, you can see how this is going to generalize to 3 dimensions. You just make the k vector a vector in 3 dimensions. The position in 3 dimensions. Dispersion relation. Now we have k squared in 3 dimensions. You can see how this goes to 3 dimensions very easily. So I won't write that down. Just add the z component. The z component for the wave vector. So it's very easy. Generalize it to 3 dimensions. Okay. So I could have just said, try this in the Schrodinger equation. And that would have gotten you to make, for this to work, then we have to satisfy the dispersion. You could have started with the original 2-dimensional Schrodinger equation. Try this to work only if this is true. But I wanted to show you the separation of variables because we're going to be using it in the case it's not quite so easy. Okay, but show you how it works in an easy case first. Yes, ma'am.
A equal the x naught times y naught times
Yeah.
y naught.
Right. So the differential equation doesn't determine those constants out front, which has to do with the probability amplitude of the wave. Right? So the Schrodinger equation, if I get a solution, I can multiply it by a constant and it's still a solution. And so this constant is not determined from the Schrodinger equation. It has to be determined from something else. to be how the thing is set up. Okay, well, actually now we could do the following scattering problem. I'm not going to do this, but it's kind of fun to think about. Let's suppose I have a hard circle. Before we had a barrier. Let's suppose now I have a hard circle. That is, the potential is infinite inside. A hard circle, potential is 0 outside. And let's make the radius of this circle, call it A. So we might have a plane wave coming in like we did before. A vector here. And scatter off of the circle. We're going to get stuff coming out. A little different than what we did in one dimension, because it has to go through the barrier. Now this can go around. So we could have maybe, instead of making it infinite, well, okay, let's tone it down a little bit. Let's give it a finite step height, not infinite. Tunnel through, but it could also go around. Interesting problem, how to solve this. Okay, so that you can see how this is getting interesting with the kind of scattering problem. This is like, hang on a second. The Rutherford problem where he shot the helium nuclei at a gold foil. The nuclei bounced off, but the helium nuclei bounced off with the nuclei in the gold foil. This is it. We're finally getting to the point where we can do that problem. Solve the Schrodinger equation. It's a scattering problem in 2 dimensions. Actually, you want to do it in 3, but you can see how you get closer. So,
would this be more along the lines how you would solve the single and double slit experiments?
yeah, that's right. Exactly. Instead of having that, you can have something like this. So these are hard. The particle can't get inside these things, but they can pass through the wave. The Schrodinger equation will have waves that pass through the slits and produce a diffraction pattern on the far side. Right. You can set it up by having a plane wave coming in, shooting electrons at this thing, and see what passes. You're going to get some things coming back, of course. But okay. Things are getting interesting. Okay, you could do bound states. So let's look at bound states in 2D. Let's do a particle. We did a particle in a box. Let's do a particle in a square. Let's make each side of the square the same length, just to make it easy to begin with. Obviously, you can do it differently, but let's make it the same for both directions. Okay, so we have the condition of the wave function. So the first thing is we're going to look at which we can get by doing separation of variables once at a time, like that. Okay, and then we have the condition that the wave function is 0 along the perimeter and 0 outside. So the only place the wave function is not 0 is inside, but when it gets to the edge, it has to vanish everywhere around the perimeter. So we want to solve them time independent Schrodinger equation. And we have that side along the edge of the square has to vanish everywhere around the edge of the square. So this is like what we did in 1 dimension for a particle in the box. Now we're going to put it in the square to see how things change. Okay, given the talk today, the theme of the talk today, what would be the approach that would be suggested? Separation of variables. Let's try. In fact, it works again. Product of two functions. Okay, I can satisfy the boundary condition. The wave functions vanish, in the individual parts vanish on their ends, on their respective ends. So if x vanishes on its ends and y vanishes on its ends, then this will vanish everywhere on the square. So we can take this edge condition and rewrite it as end conditions, like we did in the particle of the box. And then we do the separation of variables, just like what I did. Except that we got the free, we did the particle in the box, we have the free particle Schrodinger equation with boundary conditions. The wave function has to vanish at the ends. So the solution looks like this. Did before follows through. So it's just a product of one-dimensional particle in a box, wave functions. But we have two different variables. We have an integer for the x direction. We have a different variable, different integer for the y direction. So total energy then. Like this. So the end conditions mean that the wave function has to be like this. Gives you zeros on the ends. If n x and n y are positive, positive integers. Right? You see how this one makes this happen? This one makes this happen. Just like it did part of the box. So in 2 dimensions, we get this. Remember what it was in 1 dimension? It had one number, n. And this is a function, this n, t, depends on those two integers. We had a e sub n was h bar squared pi squared over 2m l squared times n squared, or n squared times t1. Now we've got the energy similar, but it's the sum of 2 squares, not just 1 square. N squared, but we've got an x squared and then y squared. Okay, so the wave function is just a product of the two particle in the box wave functions. Let's see the ground state. Let's see. We have 2 quantum numbers because we have 2-dimensional problems confined in 2 dimensions. The ground state is when they're each equal to 1, 1 and 1. What's the energy of that? It's going to be divided by h bar squared pi squared over 2 ml squared. Okay, so it's going to be 1 squared plus 1 squared. 2. What would be the next state? First excited state. And how would you get that? I guess there's like 2. We've got 2 numbers here. What if we raise one of them to be a 2? So let's suppose it's 2, 1. What's the energy of that? 5. Oh, but there's also 1, 2. Why did we pick x? We could also have picked y. Also 5. Now we've got a case where we have 2 pure modes of the same energy. The first case of the degeneracy. Well, actually, we had right and left traveling waves before had the same energy. So we did have degeneracy there. So this is maybe not the first example. Okay, what would be next? Right, we're just playing with these two numbers. All we got to do is just take combinations of these two numbers, but we want to figure out what's the spectrum. We want the next energy. Let's try 2, 2. What do we get there? We get 8. All right. What about 3, 1? Well, 3, 1 and 1, 3 are the same, and that's 10. So yeah, this would be next. Just keep going. And we have another degeneracy. So 3, 2, maybe, or 4, 1. Is 3, 2 next or 4, 1?
3, 2, and 4.
Let's see. So this is 9 plus 4 is 13. This is 16. This is 17. So this would be, so that's 13 and 17. Looks like it goes in this order. Just keeps going up. There's no limit, no bound to this because the square is infinitely hard. The potential goes up to infinity. It perfectly confines the electron inside the square. The electron can get out at all. Wave function is 0 outside. So we have this spectrum, a little different.
So are you dividing, so you're taking the E that's there and dividing it by that?
Yeah, this thing, right? Everything was a combination of this times the sum of the two integers squared. So I just divided by this, putting it in units of this. So I just have these numbers.
What's it called, a degeneracy?
Because there's more than one. More than one state at the same energy. Of degeneracy. Multiple states at the same energy. Let's speculate for just a second. I've got you about 1 minute off, but let's just speculate. Suppose it weren't a square, it was a rectangle. How would that change all of this?
Change how the L.
Now we would have to bring this L would be different for the X and the Y. So we have an NX squared over LX squared plus NY squared over LY squared. So now that would ruin the degeneracy. We wouldn't have two modes at the same energy because X and Y are different from each other. Break this degeneracy here and here. So if I stretch the square to a rectangle, then the states are no longer degenerate. You break the degeneracy by stretching the square. Okay, so you're going to do it in 3 dimensions for homework Friday. And I did go a little bit quick here, so you're not going to go that quick. You're going to follow all the steps correctly. But you can kind of imagine how it's going to turn out. 3 dimensions, they're going to put a particle in a cube. All the sides are the same. I think you could guess. You're just going to have an NZ. 3 quantum numbers, 3 dimensions, confinement in 3 dimensions, you have 3 quantum numbers. You get NX, NY, and then Z squared. Add to this. Already played with this degeneracy here. You got the sum of 3 squares. So you can kind of play with the spectrum. See how it comes out. Okay. Questions?